Hello, this is just a short video to illustrate different methods of fabrication, specifically with holes in this case. And there's a couple of videos embedded in here to show the differences between drilled holes, punched holes, and then some results of a research project that Dr. Rosati and I conducted here at the University of Cincinnati. So let's get started. The primary methods of making holes in structural steel members are by drilling and punching. Generally speaking, drilling can be used in every case, but the tooling is a little bit more expensive and it's not quite as fast as punching. Punching, on the other hand, can only be used on relatively thin material. In some cases, you'll see people say that material up to a half an inch can be punched, or maybe 3/4 of an inch thick. The rule of thumb that I generally work by is if you can have a hole that is punched through material that is no thicker than the diameter of the punch, then the punching should work. But I've heard lots of different rules of thumb for that. Thermal cutting can also be used in some cases, but again, it's a function of how thick the material is. It generally works better for thinner material than thicker material. And by thermal cutting, we mean plasma usually, but sometimes oxyacetylene can be used as well. Water jet cutting is something that can be used, but it's not used very often because it's a newer technology, and the machines that are used for water jet cutting are very, very expensive. All right, so this shows a drill press, and this is a video that I took while I was at the North American Steel Construction Conference. So this is a video that I shot using my cell phone at the North American Steel Construction Conference put on by the American Institute of Steel Construction, AISC's NASCC. And that's a conference where they do a lot of presentations and sessions and things like that for continuing education. But they also have a trade floor where manufacturers will bring in their products and show off to engineers or fabricators or whatever. So in this case, it was a company that makes equipment for fabricators, and they brought in a bunch of different equipment, actually set it up, brought in some plates, and they're illustrating how this different equipment can be used to fabricate the steel. So this is a drill press that's used to put holes into a steel plate, and it's completely automated. So they call it CNC drill press, computer numerically controlled. So they put a program in. Maybe a program like Revit would have all the connection details, and you would output that to a file or a USB drive, or maybe transfer it via network to this drill press, and then the holes would be made automatically. So there's a little thing here off to the right, and I think it's right here is an oxyacetylene torch, and I think that's what's being used to actually cut these pieces out at the end of the drilling operation. Okay, so in this case, you have a fluted drill bit that actually spins and removes the material. So the quality of hole that you get with a drilled process is about as good as you can get. And this is what a hole looks like after it's been made using a drill. So you can see the annular rings on the inside of the hole, and there's very little imperfections or flaws that are imparted on the steel during the drilling operation. Okay, the next video that I have is called an angle master. It's a general term that they have, though this company would probably cringe if they heard me use the name from a different company on their product. But basically, you run an angle through here, and this will both punch holes and then cut the angle to length afterwards. So this process is automated, and it saves a lot of time because typically angles are used as connecting elements quite often. You have an angle between the web of a beam and a column, for example. You might have the angles between the web of a beam and the supporting girder. So if you can punch holes and cut angles to length quickly with very little user input, then you have an efficient operation. So this is a shearing operation. This is one of the methods of cutting. Hopefully you've checked out the YouTube videos that show sawing, oxyacetylene cutting, and plasma cutting as well. But in this case, you basically use a shear, which works like a pair of scissors cutting paper, except that the forces are much higher and the tooling is a bit more sophisticated. So this is actually the back side of the same machine that I showed in 2 slides ago, the angle master punching. So after the angles are punched and they have the holes in them where they need, then this advances forward and the shear comes down and cuts the angle to length. So if you look at the different methods of cutting, you have a saw cut, you have oxyacetylene, you have plasma, you have this as a shear cut. They're not all equal. A shearing operation actually causes deformations and an imperfect edge, if you will. But in connecting elements like this, where you have relatively predictable conditions, there's no fatigue or anything like that, then having a sheared edge is usually just fine. So the punching operation works like this. You have a punch and a die, and the punch is just a little bit smaller in diameter than the die. And basically, it's very analogous to using a punch in to punch holes in paper. So the punch works its way down through the top and punches out a slug of material and leaves a hole. And if we were in the classroom, I would actually show you some slugs that I collected from that machine at the conference. But if you look down here at the bottom, one of the things that's interesting is that it does a pretty good job of shearing the material over about the first half of the thickness. But then after that, it starts to actually tear away at the edges. So when you look at a punched hole, you can often tell which direction the die and the punch were moving relative to each other. In this case, the punch is moving from the top down. You have a fairly well sheared surface for the first part of the hole, and then you have a torn surface for the remainder of the hole. So you can see that in this case here, we have 2 holes that were punched. And you can tell that in the case on the left, this hole was made with the punch coming up from the bottom and the die was on top. Whereas over here, you can tell that the punch came down from the top and the die was on the bottom. So, this first part here is fairly well sheared and looks like a fairly good quality hole. But then starting at about here, you can see where instead of shearing cleanly, it started to tear. And the opposite is true over here. You can see where it's sheared fairly well in this region, but then it started to tear down below. Now that tearing is detrimental to the performance of the hole, but it's detrimental in different ways. If you're doing with a static loading, like just wind, wind is. Let's not talk about wind. Sorry. If you're dealing with a static loading like dead load, live load, snow load, rain load, things like that, then it doesn't make too much difference at all. If you're dealing with a fatigue load, like putting these in a bridge, then it makes a lot of difference because then fatigue cracks can initiate in those imperfections. Now, wind, I brought that up. Wind is typically not considered a cyclic load because there just aren't enough cycles for it to become important. Yes, it's cyclic, but over the life of a structure, you might have in the hundreds or maybe 1,000 wind cycles. And in order for it to be significant, you either have to have a higher magnitude or a higher number of cycles than wind can produce. So before we move on, I wanted to point out that these 2 holes were made with a relatively new punch and die set. And the die and the punch, they wear, and as they do wear, the quality of the hole degrades. So these 2 holes were made by punching as well, but they were made with a relatively worn punch and die set. And you can see that there was a whole lot more tearing that went on in the formation of these holes than in the ones on the previous slide. So in this case, I'm going to guess that the hole was made by the punch coming up from the bottom on the left side. You can see some shearing here, but then it's basically torn. Right? And over here, I'm going to assume that it's the opposite. I'm going to assume that the punch came down from the top. I'm not positive, but I'm fairly certain because you can see this tear right there that's just horrible. All right, moving on. So you can also have thermal cut holes. And when we did our research project, we asked the fabricator for some flame cut holes. He went ahead and did that, but without us asking, used a pencil grinder to clean up the inside of the hole. So these were flame cut holes. And then he used a small grinder on the inside to remove any of the heat affected material, or at least the surface part where you get the slag effects. So we looked at a number of different cases. We have some bars. You saw some of those tests in one of our previous videos. And we used drilled holes, good punched holes, bad punched holes, and flame cut holes. And we looked at holes that were made for 1/2 inch, 3/4 inch, and 1 inch diameter bolts in 2 different grades of material, A36 and A588. Excuse me. We also looked at the T material, and the idea here was that there's some work hardening, some strain hardening that goes on in the region, which is defined as the K zone, and that's the transition between the web and the flange. That material goes through a bit of flow during the rolling process, and we thought that having that included in the experiment might affect the results. Also, we were interested in comparing the A992 material to the A36 and the A588, and the A992 material was available only in W shapes. We can't get plate or bar in A992 material. Just to keep everybody honest, more or less, we ordered the material from 2 different mills and considered the samples separately. So in this case, the holes were made for only 1 inch diameter bolts, drilled, punched, and flame cut. And then some of the specimens were strain aged. And there's a phenomenon that I'm not going to go into in much detail, but basically, if you take these holes and if you take these specimens and you punch them or subject them to a high strain event and then let them sit for a while, the behavior is different than if you punch them or subject them to a high strain event and then test them right away. And in order to simulate a period of years, we actually put them in an industrial oven and baked them basically at 350 for 3 or 4 hours. And that simulates the, I think, something like 20 years at 70 degrees Fahrenheit, something like that. So that's our test matrix for the W18 by 40 specimens. Okay, so we tested each of these and compared the results, and here's what we had to show for the bar test, the A36 bars with 3/4 inch diameter holes. So we have 4 different traces. We have one for the drilled hole shown as green. We have one for the, we have one for the drilled hole shown as blue. We have one for the flame cut holes shown as green, and then we have the good punched and the bad punched shown as purple and orange. So it's interesting, the strength up here to the yield point is not compromised at all, but you can see that there's a cutoff here with the punched holes relative to the flame cut and the drilled. Now, 2 things surprised us in this. Let me erase the ink. First is that we didn't expect the flame cut holes to perform as well as the drilled holes, and we were quite surprised by that. Pleasantly surprised, because flame cutting can be efficient and cost effective for cutting the holes, and if they behave as well as drilled holes, why then that represents an efficiency in fabrication that might be realized. The second thing that surprised us wasn't that the punched holes performed more poorly, but that the bad punched holes and the good punched holes behaved basically the same. So if you look at the holes, you have good punch, bad punch. The bad punch look a lot worse than the good punch, and they behaved basically the same. So that surprised us. Okay, here's a similar behavior except in A588 material, and in this case, the difference between the drilled and flame cut versus the punched holes is not as pronounced, but it's still there. In both cases, the drilled and the flame cut perform better than either of the punched holes. All right, now here's some of the T specimens, and so we have different traces going on here. So we have a drilled hole again shown as blue. We have flame cut as green, punched as purple, and then strain aged as orange. And it turned out that the strain aging didn't affect too much here. But it's interesting again that the drilled holes and the flame cut holes perform better than the punched holes, though not as pronounced again as what we saw with the A36 material. Okay, so in order to quantify the difference in behavior, we wanted a number that would indicate the amount of ductility that we're getting. So we defined this ductility ratio, and it's basically the deformation that we have at failure. So basically, failure, let me get my pen working, is out here, and that's the deformation at failure, delta sub U. We wanted the deformation at yield, but our stress strain curve didn't cooperate. So we basically figured out where the yield plateau was, struck a line back here, fit a line to the elastic portion, figure out what that point is there. That's the yield point, and then we have the yield deformation delta sub y. So we define the ductility ratio as the deformation at failure divided by the deformation that corresponds to yielding. So we can look at the ductility ratio for the different specimens. And you can see that for the drilled and the flame cut, we're looking at ductility ratios that are at least 30, maybe up into the 40s or 50s in some cases. Whereas when we look at the good punch or the bad punch, our ductility ratio at best is 34 and at worst is down around 11. And for the A588 material, in general, it doesn't have the same ductility, the material itself, but you can see that the drilled holes and the flame cut holes perform better than the punched holes. In fact, with the A588 material, the worst case for the drilled and the flame cut showed a ductility ratio of about 12, and the best case for the punched hole was a ductility ratio of about 10. Okay, carrying that discussion forward and looking at the T specimens where we had the A992 material. A992A was material from one mill, A992B was material from another mill. And you can see again that behavior carries through here, though it's not as pronounced with the A992 material as it is with the A36 or even the A588. But still, the drilled holes and the flame cut holes perform better. And it's interesting to note that the two materials did not necessarily perform the same. So A992B, for example, performed better, especially with the drilled and the flame cut holes, than A992A did. Now, I should mention that the hole gauge that's shown there is the distance between the holes. So 3 1/4, 3 1/2, and 3 3/4. That is important because when the hole gauge is smaller, then the holes are made closer to the K zone, the area where we had a lot of strain working or work hardening going on. All right, so that wraps up this little lecture. Like I said, it's a short lecture, talks a little bit about fabrication methods. Hopefully you can see that there's a difference between punching, drilling, and flame cutting, and we haven't tested any water jet holes yet. Now, how does this all play into your design? Well, if you're designing a building, it probably doesn't. You as the engineer are going to specify a tension member. You'll probably specify bolt diameters, things of that nature. What you probably won't do is you probably won't specify the method that's used for making the holes. That's not always the case. If you're doing something that's seismic, for example, where you have a cyclic event that is high stress, high force, even though it is a low number of cycles, then in seismic world, you're probably going to stipulate that all the holes in critical members have to be drilled and they can't be punched or flame cut. If you're dealing with bridges, then any hole that's made in a primary member typically has to either be drilled or punched to a smaller diameter and then reamed out to its final diameter. And that's because fatigue tends to drive the design of bridges more than it does for buildings. But like I said, for this class, with us looking at buildings primarily, and we're not focusing on seismic, then the amount of ductility that we get, even out of the worst hole, is still quite adequate for the needs that we have in this context. All right, take care. We'll see you again soon.